lecture we are going to introduce some basic digitization in power electronics converter. So in this course, in this lecture, we will talk about basic feedback and feed forward control, then few basic requirement with power management bus, and then basic level of digitization using housekeeping and the possibility of further digitization. So first we will talk about the control of DC-DC converter. So here I am just showing a DC-DC buck converter, but you can have any switching power converter that you can replace. So where we are sensing here, let's say output voltage you are sensing, this is my feedback voltage, you are taking the resistive divider, and then we have a current sensor also. So whether the current sensor is, it is not mandatory, it is maybe optional based on whether you are using current mode control or voltage mode control, you may or may not use. Then after this block, it is a sensing block and the signal processing, then it goes to the feedback control. That means what is the control structure? That means whether it is a linear control, are you going to use a standard current mode control, or are you going to use a state feedback control? Are you going to use the output feedback control like only voltage mode control? Are you going to use ripple based control, hysteresis control? So many possibilities exist, but ultimately end of this feedback control we need to have a modulation technique, because this will generate our duty ratio or basically the gate signal, this gate signal, and these gate signals are nothing but on off time. That means it will generate on and off time, the setup on off times. So one of such example is that is a PWM latch. That means if you are talking about fixed frequency modulation, pulse width modulation, where we compare two signal and the output of the comparator goes to the latch circuit and then latch generate the gate signal. But it is not mandatory that we need to use PWM, we can use various implementation. In fact, in this course we will be using, apart from fixed frequency also, we will be using variable frequency architecture also. Now here I am talking about a basic voltage mode control. So in the voltage mode control, we have a feedback loop and then it is compared to the reference voltage, and then the error voltage, this is the error voltage, it goes to the compensator, and the output of the compensator is compared with the sawtooth waveform. So this is our sawtooth waveform, this is our sawtooth waveform, our sawtooth signal, and then comparator output goes to the latch circuit. Okay, so here it is a pure analog control, there is no digital part, and the compensator typically used in voltage mode is a type 3 compensator, and you can see for such compensator, if you are talking about up to few megahertz or so, most of the commercial product, so this part will be the off chip product. That means we have to put it from outside separately, because their values are large and you may not be able to put it inside the IC. So it depending upon the technology. But if you go for very high switching frequency, maybe this IC, when the capacitor size will come in the range of picofarad, then only you can put it inside the IC. Okay. Now how do you start with the basic digitization? So first of all, if you look at this feedback control, so this is our reference voltage. Okay. Now this reference voltage should be programmable. Why? Because when you are talking about the dynamic voltage scaling application, or if you are talking about an envelope tracking application, because if you are talking about this DC-DC converter, suppose this is your DC-DC converter, where it is the input is like battery. So it is a battery. So input is just a battery, and the output, let us say it is driving a processor, maybe a small processor, it is a processor, and the processor voltage VDD of this processor may have to be adjusted based on the task requirement. That is one scenario. This can be also the envelope tracking power, this can be envelope tracking power amplifier, because power amplifier means which is used to, for example, for our antenna, right, for powering our that means the RF transmission, right, or the signal transmission, wireless transmission. So we need to provide sufficient power to the antenna, so the power amplifier is used, and to provide sufficient VDD, then we need to use a DC-DC converter, and the voltage of the DC-DC converter has to adaptively vary according to the envelope of this power amplifier. and then you need to change the reference voltage. For such application, how do you change VREF? So VREF programming is one requirement. The another requirement, we know constant on off time modulation. So for example, constant on time control, we need to adaptively vary on time. Okay, so how do you adapt the on time? Okay, that is one possibility. The another possibility is the power management bus. Suppose we are talking about that many converters are connected to a common bus and they are sharing data and the clock. Then for this communication, it is a digital communication, but your basic converter is loop is analog. So how to deal? So first level of VREF programming, how to do that? So as I said, this DC-DC converter is supplying a processor, but the processor task, based on the task, it will ask for a required VDD, and that is a VDD comment, and that is nothing but your reference voltage. And this comment comes from the processor as a digital number, it's just a number, and you have to convert to an analog voltage, because this reference voltage is the reference for the voltage mode control, and this whole control is analog. So you need a D2A converter. So that means overall system looks like this. So this is the processor, it is supplied by the DC-DC converter, and the processor is asking for certain voltage, and we need to program this VREF accordingly, and this whole loop is in analog. And you can see this DC-DC converter is nothing but this one, which is actually supplying the processor. So in this case, everything else is analog, but the reference voltage programming is digital. So this is a housekeeping arrangement. That means this is housekeeping, you can say housekeeping digital. That means we are not touching the basic analog feedback loop, but we are digitizing some interfacing signals so that the main loops remain analog. Another application, if we want to adaptively vary on time. So suppose we need to maintain certain switching frequency. So how to adaptively adjust on time? Because we know that constant on time, if the input voltage changes, okay, then there will be a change in the switching frequency for fixed on time. So you need to adapt the on time in such a way you can regulate the switching frequency. In such application, so how do you, that means this monoshot timer will be loaded with constant on time, but how do you update this on time? So one possibility, by means of VDD, that means suppose we need to program the VDD of this supply, okay. So that means we'll change the reference voltage, we have discussed. That means we will be using a DAC here, we will be using a DAC here, and DAC will have this information from this. So DAC will change the reference voltage. But once the reference voltage changes, and if your input voltage is fixed, then naturally switching frequency will vary. So in that case, we need to adaptively vary the on time, and that has to be loaded here. And this adaptation monoshot timer, it can be fully digital. That means you can just use either counter based or other architecture, where you can update the number. The another level of digitization is the power management bus. What is this? Here multiple converters are connected. It's like an interconnected power supply network, where we have a DC-DC converter 1, 2, n number of converters are there, and each converter is sharing data and clock. Now the clock is common, and this will help to synchronize the switching frequency and do other kind of operation. Suppose if all these converter undergoes the same switching frequency, right, or it depending upon its power stage design, the switching frequency can be different. But there are scope for optimization. Suppose each converters are rated almost the same power level, and they are operating under nominal power. That means their switching frequency are more or less fixed. Then you can shift the clock in such a way we can optimize the ripple parameter of this converter, because maybe all these converter may have a common input voltage, because in case of our mobile phone, it may be just a battery can be input. So this input each converter will have the input capacitor. So you can reduce the size of the capacitor, overall capacitor at the battery terminal, by means of sequencing this the gate signal, or basically switching signal. Similarly, if this converter, since it is driven by battery, that means you can say there is a battery here. So this can be a battery, and you can also have a cap here, bank of capacitor here. Now this battery cannot support very high current, because a battery, depending upon the battery technology, whether it is a high power density or high energy density, but still it has a limit in the current, both slew rate as well as the magnitude. But if all converter undergoes transient, then if everybody asks for high input current, then the battery can collapse. So there you need to put some kind of sequencing. So that's why this digital interface helps in many ways in power management bus. But the question is, in this power management bus, let's say each converter is running with the analog control, pure analog control, but since they have to communicate with the bus, so they need to digitize. Suppose you want to send the gates your output voltage information to the other converter, so you need to digitize, and we need to share the input voltage information. So you can use a muxing operation, and then we can use a single ADC and do that. But just for communication, this sampling requirement of the ADC may be low, because you will just send this data once in many cycle, so that may not be very fast. So it may be a low computational ADC, which you can reduce the power consumption and cost, but the basic loop is analog, which can be very high frequency. But since you are using this ADC, the next question, why not you digitize the whole loop? That means, why not you digitize the voltage as well as, so if you digitize the voltage, then this information is already available, so you can selectively send this information to the PMBus. So PMBus solution, where we have a digital interface for multiple converter connected, then for such case, if you slowly go into digital, that will further enable to take the advantage of the smart communication as well as the information system, and we can implement even many other different type of algorithm and to optimize. Because suppose you want to play with the switching frequency. Suppose if you are using this DC-DC buck converter, it is a voltage mode digital control, and if you want to improve the light load efficiency, then you need to reduce the switching frequency, or you need to go for some other control. So you can simply change the control logic inside the digital platform. Not significant changes are required, so those can be easily accommodated. So the next question, that means in the subsequent lecture, we will be slowly digitizing the feedback loop. So this is a starting point. So that means in the process of digitization, we can start with the housekeeping, which is a very nominal level of digitization around the analog loop that we have discussed, and in the subsequent lecture we will slowly digitize the feedback loop. Here we are talking about only voltage loop, single loop. If there is a two loop control, should we digitize all the two loops, or only one loop analog, one loop digital? So depending upon, there will be various architectures. So that we will be discussing. In summary, we have discussed basic feedback and feed forward control. We have identified basic requirement in case of power management bus. Then what are the basic level of digitization using housekeeping, I have also discussed, and the possibility of further digitization is also discussed. That's it for today. So thank you very much.